In this section, we want to start our work with application problems, and we're going to solve some application problems, the solutions to which depend on linear equations in one variable. Now, if you have any trouble at all with these application problems, go to the book and read that blueprint for problem solving and just take it step by step. See how many of those steps in the blueprint you can get through on each problem. You'll see the more of these problems you do, the better you get at it. Let's look at our first one. We have here that one number is 2 more than another. Their sum is 8. We want to find both numbers. So what I'm going to do is I'm going to say let's let x equal the first number, or one of the numbers. Let's let x equal the first number, and then the second number is 2 more than the first one. So then x plus 2 equals the other number. So then I look here and I see that their sum is 8. That means that when I add the two numbers together, the result is 8. So let's do that. My first number is x, plus my second number, x plus 2, must be equal to 8. Now I've got a linear equation in one variable that describes this situation. All the information in the problem here is contained in this equation, and it looks like a pretty simple one to solve. When I remove the parentheses here, I'll have x plus x, which is 2x, plus 2 is equal to 8. Now I'll add negative 2 to both sides, and I'll have 2x is equal to 6. And from that, I see that dividing both sides by 2 or multiplying both sides by 1/2, I get x is equal to 3. Then x plus 2 must be equal to 5. So my two numbers are 3 and 5. Okay, I have here 3 and 5, and I know that 5 is 2 more than 3, and their sum is equal to 8. So there's two numbers whose sum is equal to 8, where one of the numbers is 2 more than the other number. So this is the kind of problem we could have solved this really just by trial and error ourselves, but what we want to do is get used to letting x represent something that's asked for in the problem, reading the problem again, getting as much information as we can so we can write an equation that describes the situation. Once we have the equation, then we use the tools we have for solving equations to find the solution. Let's look at another problem. This is what we call an age problem, and it reads like this. Pat is 20 years older than his son Patrick. In 2 years, Pat will be twice as old as Patrick. How old are they now? Now, admittedly, not a very realistic problem. People don't talk like this to each other, but it gives us a chance to take something written in words and rewrite it in terms of an equation, then solve the equation. So we're practicing these application problems. Some of these are a little contrived to begin with, but you'll see as we go on through the book, you'll get more and more application problems that make more sense in the real world. So to solve this problem, it's an age problem. Pat is 20 years older than his son Patrick. In 2 years, Pat will be twice as old as Patrick. I like to solve these age problems with a table. So I'm going to make a table here. I'm going to put both people down, Patrick and Pat. And then, let's see, what do I have? I have their ages now, and then I have their ages in 2 years. So I'm going to say now for one column, and then in 2 years for the other. Now, I want to take x and let x represent one of the things in the problem, so let's let x be equal to Patrick's age. Then I know that Pat is 20 years older than Patrick. So if I say x is Patrick's age, then Pat's going to be x plus 20 years old. Now, I can fill in this column of the table right here just by noticing that this column is what's happening in 2 years, 2 years from now. Well, right now, Patrick is x years old, so in 2 years, he'll be x plus 2 years old. So that'll be x plus 2. And then Pat right now is x plus 20 years old, so 2 years from now, he will be 2 years older, or x plus 22 years old. Now, I look back to the problem and see what other information I'm given, and I see that in 2 years, Pat will be twice as old as Patrick. So in 2 years, Pat will be twice as old as Patrick. So that will give me an equation to solve. Pat's age, x plus 22, will be equal to 2 times Patrick's age. So there I have my equation. Let's solve it. X plus 22 will be equal to distributive property, 2 times x and 2 times 2. Okay, so I can get all the x's on one side, all the numbers on the other. I'll add negative x to both sides, so I'll have 1x over here. I'll add negative 4 to both sides, and so I'll have, 18 on that side. Let's get a little more close-up view of that and go through that again. Let's see. I want to add negative x to both sides, so I'll have 22 is equal to x plus 4. Now I'll add negative 4 to both sides, and I'll have 18 is equal to x. And so that comes out real nice. I see that Patrick is 18 years old. That's what x is equal to, Pat's age, or Patrick's age. Now to find Pat's age, I'll add 20 to that and end up with x plus 20 is equal to 38. And so that's Pat's age. And this is Patrick's age. A little messy right here, maybe Pat's age, Patrick's age, but here's the point of this. We have a little problem right here written in words we've taken, and this time with the use of a little table, just to help us organize our work, we've ended up with an equation here that describes the situation that's written in words right here. Once we have the equation, the rest is pretty easy because we know we have these skills that we've developed in the class to solve equations. Then it's just a matter of saying, okay, once we get that solution, x equal 18, what is it? In this case, it's Patrick's age. Add 20 to it, we end up with Pat's age. So one person is 38, the other person is 18. Let's go on and look at another problem. Here we have a kind of geometry problem that says the length of a rectangle is 3 inches less than twice the width. Okay, the perimeter is 54 inches, find the length and the width. So it's a geometry problem, and what I like to do with problems like this is to draw a little picture. It involves a rectangle, so let's draw a rectangle and see if we can't label the parts of the rectangle so that will help us solve this problem. So if I have a rectangle like this, I'll go back and read the problem, and it says the length of a rectangle is 3 inches less than twice the width. So the length of the rectangle is given in terms of the width. So if we say let x be equal to the width of the triangle, then the length must be 3 inches less than twice that. So twice that is 2x, 3 less than that is 2x minus 3. So what I'm doing here when I label this rectangle with an x on the width is I'm saying let's let x equal the width of the rectangle. Then the length must be 2x minus 3. We can write that out also. Let's let x equal the width. Okay, so now what I want to do is write an equation that describes this situation, and here's what I know. The perimeter is 54 inches. Well, the perimeter is going to be twice the length plus twice the width. It's once around the outside of the rectangle. So 2 times 2x minus 3 plus 2 times x must be equal to 54, the perimeter. So since the perimeter is 54, I'm going to write twice the length plus twice the width equal to 54. Okay, distributive property. Now I'll solve this equation. 2 times 2x is 4x. 2 times 3 is 6. Plus 2x is equal to 54. Okay, let's see if we can get the cameraman to change to camera 3. Thank you. So now I have 4x plus 2x is 6x minus 6 is equal to 54. Okay, to solve this, I'll add 6 to both sides of the equation. I'll end up with 6x is equal to 60. Now I'll multiply both sides by 1/6 or divide by 6, and I'll end up with x is equal to 10. Okay, so I've solved my equation. Hope that didn't fall off the screen there. X is equal to 10. And so what I have is this. X is equal to 10 means that the width of this is going to be 10. And what were the units given in? Inches. So 10 inches. And then the length is going to be 2 times that minus 3. So 2 times 10 is 20, minus 3 is 17 inches. So now let's see if this makes sense in the problem. The length of a rectangle is 3 inches less than twice the width. Well, twice the width is going to be 20. 3 inches less than that is 17. The perimeter is 54 inches. Well, 10 plus 10 plus 17 plus 17 is going to end up to be 54 inches. So I've solved my problem here by taking by drawing a picture of a rectangle here, labeling the width with x, the length with 2x minus 3, then reading the problem again and seeing that this equation right here describes everything that's written in the problem. So once I've got this equation, I solve it. X is equal to 10, that's my width, and then I put my x equal 10 back into the formula I have right here, or the expression I have right here for the length, and the length comes out to be 17 inches. Again, not a great application problem, not the kind of thing you're going to see in the real world around you, but really good practice at taking something written in words and rewriting it in terms of an equation, then solving the equation. Let's look at one more problem. This time we have a coin problem. Sue has $2.10 in dimes and nickels. If she has 9 more dimes than nickels, how many of each coin does she have? So you can see I've already set up a table here for this problem where I have the 2 columns labeled with nickels and dimes, the 2 types of coins that we have in the problem, and then over here the 2 rows are labeled with number and value. So I'm going to get one expression that has to do with the number of coins and another expression that has to do with the value of the coins. So you can see I've let x be equal to the number of nickels. So x is the number of nickels. Now she has 9 more dimes than nickels. So the number of dimes must be the number of nickels, x, plus 9. 9 more dimes than nickels. So the number of nickels is x, the number of dimes must be x plus 9. Next I want to look at the value of each of those coins. I have x nickels. Each nickel is worth 5 cents. So I'm going to write my value in terms of cents. X of these nickels, each worth 5 cents. I'm going to have 5x for the value of the nickels. Each of the dimes, I have x plus 9 dimes, each of the dimes has a value of 10 cents. So if I multiply 10 times the number of dimes, I'll end up with the value of those dimes. So this is the number of dimes, x plus 9, and this is the value of the dimes. Now, to write an equation for this situation, I see that I have a total of $2.10, which is 210 cents, and that comes from my dimes and my nickels. So here's my value in nickels, 5x, plus my value in dimes, 10 times x plus 9, and that has to come out to be the total value of the coins I have in cents. So I'll write 210 cents. So here I have my equation that describes the information that's in this problem right here. By letting x equal the number of nickels, then I have dimes as x plus 9, the value of the nickels is 5x, and the value of the dimes is this. Then I add the value of each coin, that comes out to be 210. Now I've replaced all the words in that problem with a nice equation that I can solve. Let's try it. Here I have 5x plus 10 times x is 10x. See, I've drew in these little lines here to show the distributive property, equals 210. 5x plus 10x is 15x, plus 90 is equal to 210. Okay, I'm going to subtract 90 from both sides, and so I'll end up with 15x is equal to 210 subtract 90 is going to be 120. And then the last thing I do is divide both sides by 15, or multiply both sides by 1/15, and I end up with x is equal to 8. So let's bring that up over here. I have x is equal to 8, and that means that I have 8 nickels. Then the number of dimes is 9 more than that, so 8 plus 9 is 17 dimes. Now I can check. 8 nickels is going to be worth, let's see, what? 8 times 5 is 40 cents. 17 dimes is going to be worth $1.70. $1.70 plus 40 is going to be $2.10. And 17 is 9 more than 8. So you can see that the solutions that we get check with the original words of the problem. So whenever I have these coin problems like this, I like to draw this little chart because it helps me organize my work. You may or may not want to do that. For me, it's easier to do the problem this way. Once I have the equation, remember, then the rest is all algebra. So there we have a look at solving a variety of word problems, the solutions to which depend on solving linear equations in one variable.